Hello and welcome back to my channel. Students, as you all know, we are doing a problem series, and in this problem series we have taken a topic from organic chemistry, that is general organic chemistry. In this topic we have already covered 13 problems based on stability of resonating structures, carbocations, carbene ions, aromatic behavior, anti-aromatic behavior, acidity and basicity. So straight away let us try to see what is there for us in question number 14. So as you all can see on your screen, we have a compound, and this compound I have labeled two hydrogens as A and B, and you have to assess, you have to see their acidities, okay, which is more acidic, which is less acidic. And I have already told you how to judge the acidity. In order to judge the acidity of a hydrogen, you have to take that hydrogen out as H plus. As you will do that, the atom from which it was attached will now get a minus charge. So a conjugate base will be formed, an anion will be formed, and your task will be to see the stability of that conjugate base, that anion. If that conjugate base or the anion is a stable one, more is the stability, higher is the stability of that conjugate base, more will be the acidity of the hydrogen which is attached with that carbon or that atom. So that you have to take into account. So we will take up the A case first. So as you all can see on your screen, I have taken away the hydrogen number A out, and as I took it off, it leaves a minus charge on this particular carbon. And as you all can see, this minus charge is in conjugation. How it is in conjugation? Let us try to understand. Minus, single, double. So first conjugation I am taking on the left hand side of the negative charge, and as you see this conjugation, there is a scope of delocalization, and it is good for the stability, for the health of this anion. More you delocalize the charge, higher will be the stability. So for that purpose, you have to float these electrons like this, and it will make a new pi bond, and simultaneously these pi bond will go and sit on this particular carbon. That will bring a minus charge as well as a lone pair on that carbon. As you all can see, we have drawn a resonating structure as we have spoken about. So this is the structure I am talking about. So from the conjugation, you have delocalized the minus charge, making this resonating structure. Now, is there any other possibility left? You could have delocalized the negative charge. Yes, and it's very important to see. Now, instead of delocalizing this minus charge right hand side, let us try to delocalize it left hand side. Once you see this possibility, you find that yes, it is possible. How? Minus charge, single bond, double bond. So what you have to do, you have to delocalize these electrons like this, and simultaneously these electrons will be sitting on this particular carbon, bringing a lone pair on it as well as minus formal charge. So from here, from this job, you will get a resonating structure. I have drawn this place. You can simply see a new pi bond has came. The old pi bond went away and sat on this carbon as a lone pair. Now after you have drawn this structure number 2, you should realize that you have drawn something unusual thing. What is unusual about this structure? What is a speciality of this structure? As you ponder, you find that you have got a cyclic system in this anion, and this cyclic system, you find that it is flat once you try to get the hybridization of all the atoms as per the rules I have already dealt in my previous video. You will find that all are sp2 hybridized, and on that ground you can say it's a cyclic, it's a flat particle, it's a flat section of this anion. And next you will find a cyclic conjugation. How? You can see minus, single, double, single, double. And once you have done this, students, you will find that all the atoms of this 5-membered ring are encompassed. You have taken into account. How? Minus, single, double, single, double. So in this conjugation song, you can simply see that we have taken all the 5 atoms into consideration. And if you count the number of electrons which are moving in this cycle, you will find that 2 electrons from here, 2 electrons from here, and 2 electrons from here. So altogether you will get 6 pi electrons doing cyclic conjugation, and you are now well aware of the fact that if there are 4n plus 2 pi electron doing a cyclic conjugation, as in our present case where n can be 0, 1, 2, etc. If you put n is equal to 0, it gives you value 2. If you put n is equal to 1, it gives you value 6. If you put n is equal to 2, it gives you value 10. So if 2 electrons are in cyclic conjugation, 6 electrons are in cyclic conjugation, 10 electrons, 14 electrons, those number which follow this Huckel's rule, 4n plus 2 pi rule, will be declared as aromatic in behavior. So you can understand, by drawing this structure, you have come to a very important feature of this anion. It is aromatic in nature. So aromaticity, as I have already told you, is something which gives an edge to the species, gives benefit, gives stability to that species. So it's a very good merit of this anion formed by A. Now, after discussing this, now let us come to our hydrogen number B. Once you try to remove the hydrogen number B, as you can understand, this was the position of the hydrogen number B. After removing it as H plus, you have got a minus charge. Now, if you try to find whether there is a delocalization situation present, because you should see for the delocalization. Why? Because delocalization of minus charge or plus charge brings a stability to the system. So you find that yes, there is a conjugation right there. Minus, single, double. So you can go for the resonance. You have to delocalize these electrons like this, and simultaneously you have to put these pi electron over this carbon. So once you do that, these lone pair are going to make a new pi bond. As you can see in this structure, from here to here, a new pi bond has been created, and the older pi bond is now sitting as a lone pair on this carbon, as you can see. Again, I want to emphasize a very important resonating structure which I have drawn the next. You should understand, this minus charge is again in conjugation. You can see minus, single, double. So as you see this, you can delocalize these electrons like this and put these pi electron on the nitrogen to make a further better structure. Why I am saying this? Because once you draw that, these electrons are making a pi bond. As you can see, a new pi bond has been created, and the older pi bond are now seen as a lone pair sitting on nitrogen, and now minus charge is on nitrogen is a better structure than carbon holding that minus charge. Once you arrive at this structure, you find that there is something again unusual coming to this option number B. What is that? If you try to see this particular ring, then you immediately realize that okay, it's a cyclic part. You will find that all the atoms are sp2 hybridized. So it is a flat portion of the system. And if you try to see the number of electrons, whether there is a presence of cyclic conjugation or not, you will find yes. How? Minus, single, double, single, double. So you understand, you have incorporated all the 5 atoms in the conjugation. So there is a presence of cyclic conjugation. And if you try to find the number of electrons involved, 2, 2, and from here 2. So altogether 2 plus 2, 4 plus 2, 6 pi electrons are present. So again, this particular left hand side ring is following the Huckel's rule, and there is an aromatic character. So you were overwhelmed by this property you found just now, but you have to remain very cautious that although you got glimpse of aromatic character in this anion, there is something more to this anion you should understand, and that something is you should not overlook this part as well. Once you see this part, this is also unusual feature to this anion. How? You see, it's a cyclic portion, not just cyclic, it is flat also. All the atoms are sp2 hybridized. Not just that, there is a cyclic conjugation as well. How? You can see double, single, double. So double, single, double gives you a cyclic conjugation, and all the 4 atoms of the ring are coming in the ambit of this cyclic conjugation. Now, if you count the number of pi electrons involved, once you count the number of pi electrons, students, so 2 electrons from here, 2 electrons from here, and if you add it, it gives you a figure of 4 pi electrons, and the moment you write this figure, it alarms you. What is alarming in this figure of 4 pi electron? Because you know that there is one pole which is called as aromatic behavior. There is an opposite pole also which is called as anti-aromatic. And you understand, for a species to be anti-aromatic, what are the conditions? The conditions are quite similar to the conditions required for the aromatic compound, for the aromatic species. Cyclic it should be, the part should be cyclic, flat, cyclic conjugation, but instead of 4n plus 2 rule, now you have to follow 4n pi electrons rule, where n can be not 0, it should be 1, it can be 2, 3, so on. So if you put n is equal to 1, you immediately get a figure 4 pi electrons. Okay, that was the issue I was indicating towards, that this part is basically giving you anti-aromatic character. So you should give it an important thought process that it is simultaneously showing aromatic portion also and anti-aromatic portion also. So what is the lesson to be learned from this presence of simultaneous behavior? It is aromaticity is doing good to you, anti-aromaticity is doing bad to you, and now you should understand the bad thing of the badness of anti-aromaticity is higher than the goodness of aromaticity. What I am trying to say, the anti-aromatic behavior is going to harm this anion more than the aromatic character is going to help this anion. So if you join these two features, so you will find that instead of getting stabilized, it will be destabilized. Okay, so one aromatic ring, simultaneously another presence of anti-aromatic ring. If you club these two behavior, you will get a net destabilization, and then now it becomes very easy to compare how that you know that after the removal of A, the species was purely aromatic. There was no tinge of anti-aromaticity. However, once you have removed the hydrogen number B, Then you got the goodness of aromaticity, but the bad behavior of anti-aromaticity also was in action, and it does it wipes out the goodness of the aromaticity. Okay, so that is a drawback of the removal of hydrogen number B. So now it must be very clear to all of you that A is going to be far acidic than the hydrogen number B, because the removal of A brings aromatic character. However, the removal of B brings both aromatic character as well as anti-aromatic character. So the inception of anti-aromatic character, the involvement of anti-aromatic character was a problematic element, and it does wipe out the almost wipe out the goodness of the aromaticity. So that was a huge drawback. So that is how you should keep on thinking once a problem comes in front of you. And like these, we are going to do more problems in future also, in our future problems. So till then, keep watching my videos. Try to, if for an example, if you get to see any doubt, if you have any problem with these problems, you can write in the comment section, and I will definitely going to answer those queries. So till then, take a good care of yourself. Thank you very much.